Hi, this is the page 41 video, and the purpose is to prove the Lagrange's little theorem. So this and the following videos for the rest of the RSA chapter is in some sense just if you're interested in doing the mathy, seeing the mathy stuff or knowing the details of exactly why RSA actually works. So I'm going to spend a lot of time making these videos, and it may not be worth it to you, but if so, don't watch them. So here we go. The Lagrange's little theorem says that if n is prime, then for any a in this world, we're going to call it z sub n star. Z sub n star is just a notation for everybody in z sub n, which we talked about before when we were doing the fast Fourier transform, everybody except 0. So 0 is not in there because it's just the ones that behave nicely. Okay, so for any guy, so the conclusion is, so if you have any a, then the exciting conclusion is that a raised to the n minus 1 power is equal to 1 in z sub n. So in this strange world of arithmetic where n is 0 and any multiple of n is 0, if you raise any a, non-zero a, to the n minus first power, you always get 1. So this is the fact we are using in the FFT to construct funny little worlds like Z7 and Z13 and Z17, where various nice powers of alpha were equal to 1. Okay, so here's how the proof goes. So we're first going to show that for some integer I, so our goal here is to show that a to the I equals 1 in z sub n for some I. And this is pretty easy. Well, it's not that easy, but... And then we'll go on to show that I has to be a factor of n minus 1. And we'll see what that means. Okay, so we consider the values. So we just start in like we've done before. And we compute a to the 1, a to the 2. So all this stuff is happening in a z sub n. So if we look at those guys, when we get up to a sub n, there are n values. Ah, damn it. Explain everything has a severe flaws. Okay, so there are n values, and there's only n minus 1 in possibilities, basically, in z sub n star. So you must have a repeat. So let's say that in this sequence of values, we have there's some smallest. Say we've got 1 is less equal k, which is less than j, which is less than or equal to n, with a to the k equals a to the j. And this, of course, like everything, is in z sub n. Okay. Oh, by the way, there's a technicality we'll have to mention in a minute. So we'll come back to that, I think. Okay, so in this list, there's got to be some repeats. So kind of what you might expect, for example, is that when we hit a sub n, it'll actually equal a to the 1. Okay, so to say that ak equals aj, a to the j in z sub n, means that n is a factor of a to the j minus a to the k. Oops, a to the k. There's no such thing as a sub k here. Okay, so But we can write that as, since k is smaller than j, we can write that as a to the k times a to the j minus k minus 1. So we factor a to the k out of both of these. So this is just a bunch of a's, this is a bunch of a's. And so since n is prime, and a is not equal to n, this means that n must be a factor of a to the k minus 1. Now what are we saying by that? We're saying if n is a factor of this whole number, then it must be, I mean, when you factor, this number is a product of all different sorts of prime numbers. It's prime factors, so a might have various factors. And so we've got a bunch of those factors multiplied out. There's k of each one of them. And then we got these other guys. But the point is, this part, n can't be a factor of this part, because a is smaller than n, and n is a prime number. So if you factor a and then a to the k as prime numbers, n won't be one of them. So that means that the n must be a factor of this part. Okay, that's an argument we'll use in a few places and sometimes forget to even mention. Okay, so we're just going to, for convenience, let I equal j minus k. That's the sort of the how many steps it is before we get excuse me, before we get the repeat. And what does that mean? So to say n is a factor of a to the I minus 1 is the same as saying a to the I equals 1 in z sub n. Because when we say a number, something is true in z sub n, we mean that if you throw away multiples of n as being 0, and that's true. Okay. All right. So we have in fact found a number a to the I, and if you look back, it's easy to see that 1 is less equal I, which is less than n. So the farthest, the repeats here, the AK is somewhere in here, and the AJ, and they're at least 1 apart, and most n minus 1 apart. Okay. So now we've got a really hard thing to do, a very deep thing that we'll do some bit. But first, let's go back and look at this earlier claim. So in fact, the earlier claim is not really true. And for example, in z sub 6, if you take a number like 2 and start taking its powers, 2 to the 1, so 2 to the 1, 2 to the, then 2 to the 2 will be 4, and then 2 to the third, so this is 2 to the 1, 2 to the second, so 2 to the third will be 8. But in z6, 8 is equal to 2. So in fact, we do get a repeat, but it's not, let's see. Oh yeah, so that's not a good example. So the if we try another guy, let's see. Anyway, the point is, in z sub n for n not prime, you can have a to the k. Oops. A to the k can actually end up being 0. But that can happen if n is prime, and I guess we won't bother ourselves with that. So let's go on to the new deep thing. Okay, so we're now going to introduce a really cool idea called cosets. So the coset, so we're first going to let brackets around a number a. So this is all happening in z sub n star. So this guy is all multiples of, b times brackets a is everything to the form b times a to the k, where k is equal to any number, 1, 2, 2, 2, 2, 2. So what does this mean? For example, in z sub 13, 3 brackets 2 is, what's that equal to? Well, the powers of 2, so 1 brackets 2 is easier to do. So that's just the powers of 2. So that's 2, 4, 8. The next one is 16, which is 3. And then you multiply that by 2, you get 6. Multiply that by 2, you get 12. Multiply that by 2, you get 24, which is what, 11? And then you get 22. I need my powers of 13 written down. 39, 52, 65. Okay, so you multiply 22, that's a 9, and then you get 18, which is 5, and then you get 10. Oops, 10, which is 10, and then you get 20, which is 7, and you get 14, which is 1. At that point, everything repeats. So this is a classic example. 2 is a good example of an A in Z13 where you raise it. So this is 2 to the 12th, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, so this is an example of Lagrange's theorem, but it also gives us the example of the coset idea. So 3 angle brackets 2, to go back to that one, just means 3 times each of these. So that's 6, 12, okay, 3 times 8 is 24, which is what? 11. Then we get 9, 18 is 4, 36 is 10, and then through 33 is 7, 27 is 1, 15 is 2, 30 is 4, 21 is 8, and this is 3. So in this case, it's kind of a bad example because angle brackets 2 by itself goes over all of Z13 star. And so if you take any multiple out in front, you either get the same thing. Well, here, let's try this. What about 4 angle brackets 2? If we do that, we get 8, 16 is 3, 32 is 6, 12 is 12, 24 is 11, 48 is 9, 44 is 5, 36 is 10, 20 is 7, and 40 is 1, and 28 is 2, and get rid of this now that we've admired it for a while. What the heck? Oh. It's just because it was in the way, so it would be brutal. And then this is 4. So obviously, if you use it, so let's see. So, oh wait, yeah, I'm being stupid. So they're all the same coset. No matter what number you take out in front, you get the same coset. So that's a really boring case. But there's other cases where things don't work out that well. So in Z13, let's see if we can find one that's interesting. We'll just have to experiment. So continuing in Z13, what's angle brackets 5? It'd be just my luck to get. So 5, 25 is 12. And then 5 times that is 60, which is 8. 5 times that is, yeah, there we go. So this is a much more interesting case. So 1 times the multiple powers of 5 just gives us these 4 guys. And so 2, 5, this really is the theorem. This example gives the whole idea, so it's worth doing carefully. So we multiply each of these by 2, so we get 10, 24 is 11, 16 is 3, and 2 is 2. And then if we do 10, 11, 3, or 2 times the powers of 5, we'll get this same set. And if we do 5, 12, 8, or 1, we'll get it. So let's pick a number like 4. So if you do 4 the coset 4 times the powers of 5, you get, and again I'm multiplying the ones up here, right? So I get 20, which is 7. 12 times 4 is 28, which is 2. No. Is that right? No, sorry. 24 is not 2. Sorry. That sounds ridiculous, doesn't it? So 4 times 12 is 48, which is 9. I don't know what I was saying. 4 times 8 is 32, which is 3. No, what am I doing? 4 times 8 is 32. Yes, sorry. Stupid. It's almost time to quit for the day. 4 times 8 is 32, which is 6. And 4 times 1 is 4. Okay, so at that point, we are looking at everything. So any other multiple, this is it. These are the only distinct guys, because you can see there are 12 of them. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So all 12 members of Z sub 13 star, which is guys in Z13 throwing away 0, and so it's just 1 through 12. So if you look at this set, it partitions it into 3 equal pieces. So one piece is 1, 5, the other one's 2, 5, and this is 4, 5. So it's not accident that all of these have the same cardinality and that all together they hit everybody. And that's really all the rest in the notes. The rest of the writing just proves that. So it's easy to show. You can prove pretty easily, and I'm not going to bore us doing it, that B times the multiples of A is a 1-to-1 and onto to C times the multiples of A. So it's always the case that Z sub n star is broken into equal pieces. Well, so what? Well, so I'm going to skip those details on bottom of page 41. So this shows that all these cosets have the same size, and obviously, if you take all the cosets, all the guys of the form B times A, where you take like every possibility for B, you hit everybody. Because we could have taken 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We could have used those as the front numbers, and we would have gotten, no matter which one we took, we would have gotten one of these. That may not be obvious. Like, look, if you take 7, draw a line there, but if you take 7 times the powers of 5, you get, so up here it's 35, which is 9. And at that point, we know it's going to be the same as 4 times this coset. So let's just check it out. 7 times 12 is 84, which is 78 plus 6. 7 times 8 is 56, which is 4. And 7 times 1 is 7. So you can see that I got the same 4 numbers there, that these two cosets are the same, just in a different order. So, but everybody's in some coset, and the distinct cosets all have the same cardinality, so it's easy to see that that's true. Okay, so what? So the point of that rather technical theorem is that the size, so this coset, which is just simply the powers of A to the 1, A to the 2, that guy must, the size of that must divide n minus 1. So, because this is just one of the cosets, so if this is all of Z sub n star, then this piece, the 1 times the multiples of A, is that has to be a divisor of n minus 1. Okay, I'm going to try to move things up here to give us just a little more room. I guess that worked. Okay, so let's say that oh yeah, so we're saying the size, the number of elements in 1 times this coset is I. That's what we had what we were doing on the previous part. So I divides n minus 1. And say divides means that n minus 1 is equal to d, some number d times I. So then we get what we want, because then a to the n minus 1 is equal to a to the d times I. And then the cool thing is we can put that's a to the I to the d, which is 1 to the d, which is 1 in z sub n star. Sorry, just in z sub n. Doesn't make sense to say z sub n star. Okay, so that concludes this little video, which has gotten really too long already. And because the embedded exercise 29 we've already done up here when we're talking about z sub 13 star and the various cosets partitioning it. Okay, so that's it for this one, and we'll now move on to another video. Thanks.